Okay, so in this video, I'm going to talk about graphs of polynomial functions, turning points, and end behavior. So I think the best way to explain this actually is to explore a few graphs, and we're going to be like mathematical explorers. We're going on a math safari. All right, so, okay. I have a couple functions graphed here. These are from desmos.com. So really, we want to explore this and notice some patterns. So this is the graph, this crazy polynomial, but this is how that polynomial factors, okay? So, okay, check this out. This polynomial has x-intercepts at -2, and I just want to point that out, -2. Notice how that x-intercept goes in hand with the 0 of this polynomial. It has an x-intercept at 1, and then it has an x-intercept at 3. That is not a coincidence. And then the other thing that I want to point out here as we're exploring this, so this is x cubed. So think about what the graph of x cubed normally looks like. X cubed looks like this. So notice that this graph is kind of like the base graph of x cubed, except it's just been pulled a little bit in more extreme directions, right? But ultimately it still goes this direction and this direction, just like the original graph of x cubed. And then just notice how often it turns. 1, 2. Those number of, that's what's known as turning points. We'll formalize that in a second. But those number of turning points, those are not a coincidence. The way that the graph turns is it actually aligns with like the zeros. So if you know how a particular polynomial factors, you actually have a lot of hints as to what the graph is going to look like. Now that's just our first one. So let's continue our mathematical safari. Okay, so next I have this x to the 5th crazy looking polynomial. Okay, so first of all, x to the 5th, I talked about this in another video. X to the 5th kind of looks like this. Okay, that's what the normal graph of just x to the 5th looks like. Now, this graph is interesting for several reasons. So it turns 1 2 times. Okay. And we have the factorization here. So I want to point a few things out. So once again, notice, so I have an x-intercept at 1. There we go. And then I have another x-intercept at 3. So the x-intercepts align with how this is factored. But the curveball here is that 2 of my zeros in this case are imaginary numbers. And so what we have here is we have this like turning point that like there's no way for this graph to go through this. So the graph instead just does this like random turning point kind of somewhere in the middle. That is common. That is something common that you see when you have imaginary numbers. So notice that I have ultimately just these 2 real numbers as my x-intercepts. And so then I have 1, 2 turning points. So there is, again, there's like a pattern here. We're trying to figure it out right now. So I'm just going to point that out and let that simmer in the back of your head. Okay, something else kind of cool here. Kind of cool. Okay. This 0, this is x minus 3 squared. This is what's known as a multiplicity. So this 0 repeats. And we call this a multiplicity of 2. So 3 has a multiplicity of 2 is what we would say. And what's really interesting is that at 3, do you notice the shape, that like the micro shape that this graph takes at that 0? At this point, it looks like a parabola. It's kind of like mimicking the behavior of a parabola, like what you would expect, right, if I just had x minus 3 squared. So this is another interesting thing that happens with these graphs. So we don't know everything with this yet, but we're just kind of exploring here, and this is an interesting thing to notice. This is squared. This looks like a parabola. Okay, let's keep going. Okay, so I've got another one here. I've got 4 of these. So I think like after you look at 4 of these, you actually get a pretty good sense of this. And I just went ahead and put this in the factored form. Okay, so in this case, so I have an x-intercept at 2, -2. So there's that one. So notice how the graph just goes whoop, straight through, okay, at 2. The next x-intercept I have is here at -1. Look at what's happening at -1. It's going zoop, zoop. It's acting like x to the 3rd. It kind of mimics that behavior, right, at that 0. And -1 has a multiplicity of 3. So these two things, they are related, right? It looks kind of like x to the 3rd, has a multiplicity of 3. It, like, all of those things are connected. So I think you're starting to see a pattern here. I hope, anyways. Next, the last 0 I have is, or 0 or x-intercept is 2. Boom. That has a multiplicity of 2, and once again, it acts like a parabola there. This is pretty darn neat. Now, the last thing that I want to point out here is the degree. So what is the degree of this polynomial? How do you figure that out? So the degree of this polynomial is found by, so this is 2 plus 3 plus 1. So the degree of this, you just add up all the multiplicities of your zeros or your factors. So this is a degree 6 polynomial. So think of how a degree 6 polynomial looks. The standard degree 6 polynomial, let's see, that was a terrible one, looks like this, right? This would be x to the 6th. So I just want to point out that the ends are both going up just like x to the 6th would. Interesting. Last one, I promise, then we will actually get into this. But I think you're starting to see, at least I hope you're starting to see some of the patterns here. Okay, so one more time. One more time. I don't know the rights to that music. I'm probably going to get this video taken down from YouTube now. Okay, so -1 right here. That's the first x-intercept. So notice it goes zoop, straight through, and that only has a multiplicity of 1. Makes sense. So as I continue on here and I come up to 1, this acts like a parabola, right? So I would assume this one has a multiplicity of 2, and cha-ching, it does. Okay, cool. And now this last one at 2, once again, we're going zoop right through, has a multiplicity of 1. It all makes sense. What is the degree of this polynomial, my friends? So the degree is 2 plus 1 plus 1, so it's 4. So what does x to the 4th look like? It looks like this. So notice the ends of this still mimic x to the 4th. Okay, so I think like this was a bunch of graphs, but I think you actually see some really powerful patterns. Okay, so let's talk about a few things now, a few terms I've been using. Okay, so first of all, turning points. A degree n polynomial will have at most n minus 1 turning points with a turn between each pair of zeros. So we've seen this. So between each pair of zeros, you will expect, so if I have a graph, here's a 0, here's a 0, somewhere between there I expect a turn. Okay, that's what this is getting at. Now you could have, this could turn in a couple different ways, but you know, you'll expect a turn in between the points. The other thing I want to talk to you about is end behavior. So end behavior is determined by the dominating term. We've kind of been referring to this, but I'm just going to formalize this. So what do I mean by dominating term? Like, this is going to take me a second to explain. So this is determined by the dominating term. So if I have some polynomial of this form, so this is going to be the term of highest degree with its leading coefficient. This is what's known as the dominating term. Okay, so end behavior then is determined by this dominating term. We'll call it a sub n, x sub n. Okay, so if n is an even number and the number in front, the leading coefficient, is positive, so this should make sense. It's going to act like x squared, x to the 4th. It's going to have both ends going up. But if n is even and the leading coefficient is negative, then you would expect it to point both ends pointing down. Now, if n is odd, it's going to act kind of like the ends of how we think of x to the 3rd, as long as the leading coefficient is positive. zoop, zoop. If n is odd but the leading coefficient is negative, then it gets flipped. So if you know what the dominating term is, you know how the ends of the function are going to behave. Okay, so just to kind of hammer these two definitions home, I just want to determine the number of maximum turning points. So that's like maximum possible turning points. It doesn't mean you have to have this many, but just the max number. And then what is the end behavior of each function? Okay, so with this one, so this is x squared. So the number of turning points, and let me change my pen color. So let's see, I'll just call it turn points. Okay, so the maximum number of turning points would just be 1. So that makes sense, right? Because it's a parabola. We know it's a parabola, so it's really just going to have this one turn. And then the end behavior. So this is just plain old x squared. So this is actually the end behavior, right? So the way that I would describe the end behavior, boom and boom, there you go. Okay, so that's the first one. Let's try another one. Okay, so here is a fully factored polynomial. What is the degree of this? You have to figure that out before you can figure out turning points. So the degree of this is found, well, we already talked about this, right? So you add up the different multiplicities. So the degree of this is 3. So the maximum number of turning points would be 3 minus 1. So at most, this graph could do something like this. 1, 2 turning points. And then once again, so I just kind of described the end behavior. So the end behavior in this case, since it's a degree 3 polynomial, and there's no like negative in the front of this, the end behavior is going to look like this, okay? All right, so one more. I actually think you should try this one. You should try it. The worst that happens is you get it wrong, which is really not that bad. Hit play when you're ready. Okay, so I've got to figure out the degree of this. This one is actually a tricky degree because did you remember this x here? This is actually one of the factors. This has a multiplicity of 1. Okay, so it's 1 plus 4 plus 3 plus 1. So that was a tricky one. So if I tricked you, I kind of baited you for that actually. Okay, so this is a degree 9 polynomial, which would mean then that the number of turning points is 9 minus 1 equals 8. Okay, so degree 9, but notice this negative 1/2 in the front. So what that's going to do is normally, so this is a normal x to the 9th, a normal x to the 9th would look like this. But because we have this negative in front here, it's going to flip the graph. So the end behavior in this case goes like this. And by the way, if you ended up getting this one wrong and you're like, oh, this is why I just want to watch the video, so just keep in mind, you are far more likely to remember this if you got it wrong than if you just watched me do it right and then you don't remember the nuance of why this worked. Instead, you will remember, oh yeah, I thought this and now I get why that doesn't work, and you just remember it better. So it's a lot better just to engage with the video, okay? All right, so now let's talk about, let me go to this list first. Graphing a polynomial. Okay, so to graph a polynomial, the first thing that you have to do is you have to find all the zeros and plot the corresponding x-intercepts. Yeah, so that can be some work, right? We've done some other videos of finding zeros. So all that work now comes into play. Then you want to find the y-intercept, and then you want to use end behavior, turning points, find any other points that you need, all that stuff. So let's just jump right into this, okay? Okay, so there's good news with this particular polynomial. So I have to find the zeros of this, but I notice that I can actually use some factoring tricks here. Do you see what the factoring trick is? So sometimes with these polynomials, you have to just like bust out, rational zeros theorem, go through all this work of trying to guess zeros, all that stuff. Every once in a while, though, you get thrown something where you can actually factor it. So I can use grouping. Remember grouping? So what do I factor out of the first two terms? The first two terms have in common x squared, so this becomes x minus 1. And then the second two terms, so I want to factor out negative 4. Now be careful, when I factor out the negative, this becomes positive and this sign should flip. So now I can finish grouping this. So since these both have x minus 1 in common, I'm going to write x minus 1 down first. And then I've got x squared and minus 4, so that's going to be my other factor. And notice that x squared minus 4 will factor right into x, so we still have x minus 1. This is x minus 2 and x plus 2. And now I have actually a lot of information that I need. So one, I have my zeros. The zeros in this case are 1, 2, and negative 2. So I just take the opposite sign of each factor. And related to that are my x-intercepts. My x-intercepts are 1, 0, 2, 0, and negative 2, 0. So you're probably noticing there is a relationship between factors, zeros, and x-intercepts. They really are all interchangeable, and just depending on which one you're talking about, you just make like a slight tweak to how you represent it. The other thing that we need to find is the y-intercept. So to find the y-intercept, I just plug 0 into my function, and plugging 0 into this function, I have 0 minus 0 minus 0 plus 4. So that's just going to equal 4, right? So my y-intercept is 0, 4. Cool, so I have a whole lot of information now. Just a few other things I want to figure out. How many turning points am I going to have? Well, I have a turning point between each set of x-intercepts, so I'm going to have 1, 2 turning points. So I'm going to have 2 turning points. And then for my end behavior, so my dominating term is x cubed. So this function's ends are going to act like x cubed. So the end behavior is going to go like this. Okay, so let's make some space now and let's summarize all this information and graph this. Okay, so I've got everything summarized here. So the first thing that I'm going to do is I'm going to just plot all of these points. So let's see, I've got 2, 0, 1, 0, negative 2, 0, and 0, 4. Okay, so the next thing that I want to do is I want to bring the end behavior into this. So remember, my end behavior, I'm going to start down here. Remember, I go down this direction. So I'm going to start down here. So what I want to do is I need to go from here to here and have a turning point. I'm going to make that turning point go through the y-intercept. So here's what I'm going to do. I'm going to go up this way. I know I need to hit this y-intercept, and then I need to go through this point. Now between these two x-intercepts, I need another turning point, and then I need the proper end behavior. Okay, you see how that works? So I've got my graph. Let's just quickly compare it to what the real graph looks like. Okay, so here I went to Desmos and I just pulled a graph of what the actual graph looks like. So we got the general shape, although you'll notice with my approximation, it's not exactly the same. Where the actual turning point occurs is not perfect. So why, or how do we make this better? All right, so the way that you make this better is you use calculus. And, you know, otherwise, if we're just at pre-calculus levels, the way that it stands, there's no great way for us to figure out like where these peaks are beyond just plugging in a bunch of points and trying to figure it out. So at least if you're in my class, I'm good right now with just like the approximate graph. This is good enough kind of for our purposes. You get the idea of what the general shape should look like. And if you're moving on to calculus, you will, spoiler alert, I hate to spoil the surprise of calculus, but you will actually learn how to draw this beautiful, perfect graph. I'm very excited for you. Okay, so let's do this one more time. So now I have a fully factored polynomial, which is quite honestly very nice. So it just really cuts down on a lot of work. So when you have a fully factored polynomial, so you do have to figure out the degree. So what's the degree of this? Let's see. It's going to be 1 plus 2 plus 1, which is 4. Okay, so the degree is 4. So that's just going to help me to figure out a couple of things. I can tell the x-intercepts just by looking at this because I can see what the zeros are. So the first 0 is -1, which means that the x-intercept is -1, 0. The next 0 is 2, right? It's going to be the opposite sign of this factor. So the next x-intercept will be 2, 0, and then the last x-intercept will be 3, 0. Now my y-intercept is found by plugging in 0. This actually will take a little bit of work. So I'm going to have negative, so if I just have a bunch of zeros, this becomes negative times 1 times -2 squared times -3. So the zeros just reduce us to those numbers. So then we just have to figure this out. So let's see, this becomes -4 times -3. So this will become +12. Okay, and okay, so now how many turning points am I going to have? I'm going to have one turn in between each set of x-intercepts. So I have one turn, two turns. So I have turning points. I'm going to have 2 in total. This makes sense because remember at 2, so maybe I'll just note this. So at 2, 0, you're going to have a parabola shape. So I'll just note that. And then my end behavior. So this is a degree 4 polynomial, but there is a negative in front. So normally this would be how x to the 4th works, but since it's negative, it's going to work. This is negative x to the 4th. So my end behavior is going to go like this. Okay, so that's a lot of information. So let's summarize it all and let's graph it. Okay, so here's everything that we're going to work with. So I'll set up a graph. And I'm going to plot all my points. So I've got -1, 0, 2, 0, 3, 0, 0, 12. Okay, so I know that my end behavior needs to go down, and then I need the 2 turning points. So the other thing that I want to make sure of is at this point here, at 2, we need a parabola shape. So either up or down. So we're just, oops, sorry, at this point here at 2. So we're going to just kind of figure this out as we go. Okay, so the end behavior. So I need to start down. So I'm going to go through this point here, and I'll just go ahead and go through the y-intercept. Now, watch what I'm going to do. At 2, I want to have a parabola shape. And so the way that this has kind of worked out, I've got my end behavior honored. I've gone through the y-intercept. So now here I am coming to 2. So now naturally, so that I can hit that multiplicity of 2, I have to make it kind of look parabola shaped. What I'm going to do is I'm just going to turn, and then I'm going to turn again. Boom. And now I've met all of the end behavior. So I've got a turn here and a turn here. And then I do have a turning point at 2, but it's more like something to kind of honor the shape of that parabola. And so again, this is just a nice approximation of what's going on with the polynomial. Okay, so those are all the examples I'm going to do in this video. I have an example video with more graphs if you want to see more, so be sure to check that out. The last thing I just want to leave you with is that, so if f of x is a polynomial and c0 is an x-intercept, so just I want to reiterate this relationship. You can have that c is a 0, c is a solution to this equation, f of x equals 0, and x minus c is also a factor of x. So zeros, solutions, factors, and x-intercepts, they all have this overlap, and the way that you refer to them is just dependent on the context, okay? All right, and so that brings us to the end of this video. Like I said, if you're looking for more examples, be sure to check out my example video. Otherwise, I'll catch you guys in the next video. Thanks for watching.